So, very good morning to all. So, is it visible the screen? Okay. So, in the last class, we discussed about the line equation of a transmission line with different parameters like a lossless transmission line, distortionless transmission lines, and lossy transmission lines. Now, based on that different transmission line, the characteristics impedance can be defined by just 1 minute. So the characteristics impedance is defined based on the voltage and current of a transmission lines. Any transmission line, either lossy transmission line or lossless transmission line or distortionless transmission lines. Now, this characteristics impedance is depends only on the geometry and dielectrics, okay, and it does not depends on the function of the length. So the characteristics impedance does not depends on the function of the length. Okay, so the unit of characteristics impedance is in ohms, but it is not same as the resistance of the wire in transmission lines, because the wire is a only resistive component. So that's why the resistance of the wire is in ohms, but in transmission line it has both inductive component and capacitive components. So by including that inductive and capacitive components, the characteristics impedance is in ohms, but it is not equal to resistance values. Now, so the characteristic impedance Z naught is equals to V of Z divided by the I of Z. That is the ratio of V of Z to I of Z values. So V of Z is the voltage applied to this transmission line, and I of Z is the current passing through that transmission lines. Now, now the transmission lines gamma into V of Z is equals to minus of R plus J omega L into current, and similarly in terms of Kirchhoff current law, gamma into I of Z is equals to minus of G plus J omega C into E of Z. So while so the characteristics impedance is defined by V of Z naught is equals to V of Z divided by the I of Z component. So V of Z, so V of Z divided by I of Z is equals to this gamma value, and this gamma value is cancelled. Therefore, minus of R plus J omega L divided by minus J omega C. Yes, we are waiting for it will come. So therefore, V of Z divided by I of Z is equals to minus of R plus J omega L whole divided by minus of G plus J omega C. So minus minus cancels. Then you can cross multiply this Vz into Vz squares, so this V of Z and this V of Z and I of Z into I of Z. So V of Z whole square divided by I of Z whole square is equals to R plus J omega divided by G plus J omega C. So this square again you can take this side, then it will comes V of Z by I of Z is equals to square root of. Okay, so where Z naught is, so V of Z by I of Z is equals to what will comes, that is nothing but the characteristics impedance Z naught value. So Z naught is the characteristics impedance and R is equals to conductor resistance in ohms per unit length, and L is equals to inductance in Henry per unit length, and G is equals to dielectric conductance in Siemens in mho per unit length. So the dielectric conductance is measured in terms of mhos. Okay, and capacitance is in farad per unit length. Now, for a radio frequency transmission lines, so radio frequency range, so radio frequency line is nothing but it will transferring the radio frequency that is 3 to 330 gigahertz of frequencies. Okay? So RF line R and G are 0. So it is valid only for high RF frequency component. So if R and G is equals to 0, what will happen? This R is equals to 0 and G is equals to 0. Therefore, J omega L divided by J omega C. So it will comes J omega cancel. So it will comes L by C. Okay. Therefore, Z naught is equals to square root of L by C. Okay. So the characteristics impedance is dependent on square root of inductance and capacitance. Now, these characteristics impedance depends upon the different length of the transmission lines, that is a half wave lambda by 2 or lambda by 4 and lambda transmission lines. So for quarter wave transformers, then this Z naught is the input impedance and Zn is the input impedance. Sorry, Z naught is the characteristics impedance and Zn is the input impedance, and Z of T is the terminal impedance, and Z of L is nothing but the load impedances. Now, therefore, based on this, so Z of T is the terminal impedances that it will be connected at a distance of lambda by 4, because of the title itself indicating quarter waves. So that is nothing but lambda by 4. Okay, therefore Zn is equals to Z of T whole square whole divided by Z of L. Z of T is nothing but the terminal impedances divided by load impedance, that is equals to Z naught value. Therefore Z of T is equals to, while cross multiplying these two, so cross multiplying these two, I think somebody joined. Okay. So while cross multiplying these two terms, then so Z of T whole square is equals to Z naught into Z of L. Therefore, Z of T is equals to square root of Z naught into Z of L. Okay. Now, this is the terminal impedance of a quarter wave transformers. So the terminal impedance of a quarter wave transformer is directly proportional to the square of characteristics impedance Z naught value and load impedances. Now, the drawback or the disadvantage of this quarter wave transformer is a frequency dependent. So, it is a frequency dependent. Now, this technique needs special line with a different characteristics impedance for every load impedance to be matched. So because this quarter wave transformer is a frequency dependent and this, so that's why every it is the characteristics impedance is the different for every load impedance to be matched. Okay. Now, so due to this quarter transformer, it is a improper mismatching, impedance mismatching. Because of it is a different characteristics impedance of every load. Whenever this load impedance is equals to the input impedance, then only the maximum power will be transferred. So these drawbacks can be overcome by using the stubs. That is the STUBS stubs. Now these stubs are connected in between this characteristics impedance and the load, either in terms of admittances or in terms of impedances. In terms of admittances, then we can connecting these stubs in parallel of the two wide transmission lines, whereas stubs are connected in series combination in while considering of the impedances of the transmission line. Now see here the steps is connecting here in parallel to this transmission line at a distance of d from the load. Here also in parallel combination will consider of admittances, whereas in terms of impedances these steps are connected in series combination from the load side at a distance of d. Okay. Here suppose if this admittances we can convert into impedance, then y is equals to 1 by z. Whereas in impedances convert into admittance, that impedance z is equals to inversely proportional to the admittance. So z is equals to 1 by y or y is equals to 1 by z. Now here the length of the stubs is, this length of the stub is L. Here also the length of the stubs is L. So either you can connecting either open circuit or short circuit stubs, whatever may be. That depends upon the applications. Okay. Now here you can see. So this is the main transmission lines. So this is the main transmission line with the characteristics impedance is Z0 value. Then this is the stubs connecting at a distance of D from the load lines and the length is L of the stubs. Now this stub matching okay. Now, here the current passing through these stubs is I of L, I of S, and I of T. Now, here, if it is these stubs is either open circuit or short circuit. Now, we use the short circuit or open circuit transmission line for impedance matching so that the load seen by the main transmission line is Z0 values. Now, first, how to connecting these stubs in a transmission line to match this load impedance is equals to the characteristics impedance of Z naught value. First, identify the length on the main transmission line from the load. Okay, so you can identifying the distance at what distance these stuffs are connecting from the load. Okay, sir. So from the load I of S at which the admittance is given by, so Y into I of S 1 is equals to Y naught plus JB. Okay, so Y naught is nothing but that is the output impedances, sorry, output admittances. Okay, so that Y naught is equals to 1 by Z naught. Now at this length, L of S, a lossless short circuit or open circuit transmission line is placed and its length is tuned to I of T, that is I of T, to have the admittance minus JB, J beta, so that so Y into I of S is equals to Y naught plus J beta minus J beta. So J beta cancels. So it will comes Y naught value. Okay. Therefore, the output admittance here is equals to the this admittance until length of LS1. Now, if it is a open circuit or short circuit, see already we told that we can using either short circuit or open circuit. If it is a short circuit transmission line, then ZSC is equals to J Z naught tan beta L. Okay, then corresponding admittance YSC is equals to 1 divided by J into Z naught tan beta L. Okay. Then the corresponding, if the steps is in open circuit, ZOC is equals to minus of J Z naught cot beta L. Okay. Therefore, the corresponding admittance is YOC, that is open circuit admittance, and ZOC open circuit impedance. So open circuit admittance is equals to inversely proportionals of admittance impedances. So that is equals to 1 by minus J Z naught cot beta L. Okay. So this is the short circuit admittances and open circuit admittances. Okay. Next. So this here we can using only one steps. Suppose even though the steps impedance matching cannot achieve, then we can using one more steps, that is the double stub matching. Okay, that is impedance matching, that is double stubs. That is we can using the two stubs at two different lengths from the load side, not from the source. Okay, so this red color indicating the stubs, that is stub 1 and stubs 2. The length of stub 1 is L stub 1 and length of stubs 2 is equals is L stubs 2, and the distance from this load is D stub 1 and distance from the second stub is D stubs 2. Now, so first we can inserting this stub 1 from the load, that is the resistive load, that is Z of R, corresponding admittances Y of R is equals to inversely proportionals of 1 by Z of R. Now, while inserting these stubs from the load at a distance of D, then even though the impedance are not match, then we can inserting one more stubs from the at the distance from the load, that is DS2, that is D stubs 2. Okay, now the impedance matching can be achieved by inserting two stubs at a specified locations along the transmission lines as shown in the above figures. Now, There are two design parameters for double stub matching. So first one is the length of the first stub line is L stub 1, that is this one, L stub 1. Okay. Now the length of the second stub line is L stub 2. This is the length of the stub, not for the distance. Okay. Next. In double stub configuration, the stubs are inserted at predetermined locations. So we are not inserting the stubs at our requirement. So first we can calculating the distance. So at what distance we can inserting the stubs, then only the output impedance is equals to the characteristics impedance, that is Z naught is equals to Z of L. So first we have to determine the distances. At what distance the stubs are connected. Now in this way, if the load impedance is changed, one simple has to replacing the stubs with another set of different length. Now, first we are connecting the stubs in some other locations. For example, you are connecting the stubs at this point. So you are connecting the stubs is at this point here from this load. Then you can calculating the impedances. If the impedance is not matching, then you can moving the stubs in another point, that is this point. Even though the stubs are not, even though the impedances is not equal, then again you can move. Okay. So at one particular, if the load impedance is changed, then one simple has to replacing the stubs. So no need to changing the load impedances. Always it is impossible to change every time the load impedance. So the simple way to comp- to equate the load impedances and characteristics impedance, simply you can replace move the stubs. Okay, replacing the stuff with another set of different lengths. That is the second step you can inserting in some other distances. Now, the drawback of double stub steering is that a certain range of load admittances cannot be matched once the stub locations are fixed. So sometimes the load impedances are not equal or not match, even though if you are inserting the stubs at a fixed locations. So there is no fixed locations for inserting the stubs. So we need to move the stubs at a different points until the it will equating the load impedances to the Z naught values. Okay. Now three stubs are necessary to guarantee that match is always possible. Okay, so while inserting 1 and 2 is not possible, but three steps are necessary to guarantee that the match is always possible. That is, matching is possible while you are using the three steps. Next, the length of the first step is selected so that the admittance at the location of the second step, that is before the second step is inserted, has a real part equal to the characteristics admittance of the lines. See here, the length of the first stub is selected so that the admittance or the location of the second stub before the second stub is inserted has a real part that will be equal to the characteristics admittance, that is y naught values. Okay? No. Now So if it is now, that is shorted lines. So the equivalent circuit of a MOSFETs of a shorted lines. Now the shorted transmission lines is shown in figure where I of S and I of R are the sending and receiving end currents. That is nothing. Here, see, this is the I of S current and this is the I of R current. Okay, I of R current. Here it can pass in the I of R current. Now here V of S is the source voltage and V of R is the V of R is the receiving end voltage and V of S is the source voltage. Now the circuit is solved by a simple series AC circuit. Now these are all connected in series combination. Okay, this circuit is a series combination because of the output is a short circuited. Now therefore the source current is equals to receiving current and V of S source voltage is equals to receiving voltage V of R plus I of R into this value, this resistance value. Okay, that is equals to Z. So V of S is equals to this voltage I into Z plus V of R. Okay. Now here while calculating the different input impedances at a different length, that is Z in of L. Okay, input impedance of a length L for either lossy transmission line or lossless transmission lines. Now, if it is a lossy transmission lines, then Zin of L is equals to Z naught into, this is the direct equation, okay? Z naught into Z of L plus Z naught into tan gamma L whole divided by Z naught plus Z of L tan H gamma L. Here Z naught is the characteristic impedance and Z of L is the impedances at a length of L plus Z naught is the characteristic impedance tan H, that is hyperbolic functions, gamma propagation constant until length of L. So gamma is equals to, already we know, alpha plus J beta, where alpha is the attenuation constant and beta is phase constant. Okay. Then this is for lossy transmission line. For a lossless transmission line, the same input impedance of a length is can define Z in of L is equals to Z naught into Z of L plus J into Z naught tan beta L whole divided by Z naught plus J ZL tan beta L. Okay, here in the lossy transmission line, we can consider the gamma, that is alpha plus J beta. Alpha is the attenuation constant and beta is the phase constant. But in the lossless transmission line, alpha is equals to 0. There is no attenuations because it is a lossless. Okay, therefore that's why here you can consider only alpha plus j beta. So alpha is equals to 0. Then it will consider only the tan beta L component, that is imaginary component. Okay, now for a short circuit transmission lines, ZSC is equals to Zn with load is equals to 0 because the output is a short circuited transmission line. So therefore Z of L is equals to 0. Therefore, so what about this equation? So Z in with Z of L is equals to 0 is equals to, then what will happen? Z naught into J, this Z of L is equals to 0. Okay, so this Z of L is equals to 0, then it becomes J Z naught tan beta L whole divided by Z naught value, because of this value is equals to 0 Z of L. So Z naught cancels, Therefore, ZSC, short circuited transmission line, is equals to, for a lossless, is equals to J Z naught into tan beta L. Okay, so beta is a phase constant and L is the length of the transmission lines. Now, from these equations, then the reflection coefficient delta L is equals to Z of L minus Z naught divided by Z of L plus Z naught. Okay, this is the general expression of the reflection coefficient. Okay, delta L is equals to Z of L minus Z naught divided by Z of L plus Z naught. Now, for a short circuit transmission line, Z of L is equals to what? Z of L is equals to 0. Therefore, what will happen? This Z of L is equals to 0 and this Z of L is equals to 0. So, whatever the remaining terms, only minus Z naught divided by plus Z naught. So, Z naught cancel, it will comes minus 1. Okay, so therefore, the reflection coefficient for a short circuit transmission line is equals to minus 1. Now, once you can find out this reflection coefficient, then the standing wave ratio SWR is equals to 1 plus del of L divided by 1 minus del of L. Now you can substituting this del of L, that is the reflection coefficient for a transmission line. What is the value of reflection coefficient of a transmission? Short circuited transmission line is minus 1. So 1 minus 1, 1 plus minus 1, this is the model. This is the model. Okay. So while substituting 1 plus minus 1 mod value whole divided by 1 minus of minus 1 mod value. So 1 plus, so minus 1 mod value, what will happen? That is equals to 1. So 1 plus 1, 2 divided by 1 minus 1. 1 minus 1 is 0. So anything by 0, that is nothing but infinity. Okay. So therefore, we can conclude that for a short circuit transmission lines, the reflection coefficient delta L is equals to minus 1 and voltage standing wave ratio is equals to infinity. Okay. Next. Now, now it is open circuit transmission lines. So for a open circuit transmission lines, the condition is Z of L is equals to infinity. So in the short circuit transmission line, Z of L is equals to 0. Okay, 0 because of current is maximum. Short circuit voltage is 0 and current is maximum. So therefore load impedance is equals to 0. Whereas in open circuit, current is 0. When the current is 0, the resistance value is equals to infinity. Okay? So that is Z of L is equals to infinity. Now, from the recalling the previous expression, Zn is equals to Z naught into Z of L plus J Z naught tan beta L divided by Z naught plus J Z of L tan beta L. Now, while substituting this Z of L in this expression directly, then what will happen? This Z of L is equals to infinity. Z of L is equals to infinity, and here also Z of L is equals to infinity. Then infinity plus anything is equals to infinity, and here also infinity plus this one is equals to infinity. So infinity by infinity, then it will comes undefined functions. Okay, that's why directly we can't substituting this Z of L is equals to infinity in these expressions. So then what we can do? Now first we can take the Z of L is common in both numerator and denominator. Then while taking the Z of L in the numerator, then what will happen? Z of L is taken out, then it becomes 1 plus J into Z of L divided by Z naught into tan beta L whole divided by, in the denominator also you can take Z of L is common. So Z naught by Z of L plus J into tan beta L. Now Z of L cancels. Now you can substituting Z of L is equals to infinity in this expression. Okay, so at the time what will happen? 1 plus, so in the front side Z naught as it is, so 1 plus Z of L divided by infinity. So anything by infinity that is equals to 0. Then Z naught by Z of L that is also equals to 0. So anything by infinity is 0 plus J tan beta L. So what will happen? 1 divided, so this term is 0, this term is 0. So remaining terms is Z naught as it is divided by 1 by J tan beta L, or 1 by tan, you can write it as cot. So you can take J in the numerator and denominator. So J and minus it will comes. So while adding the J and numerator and denominator, J square is equals to minus 1. So minus into J, 1 by tan is cot. Z naught is as it is. Therefore, the characteristics impedance for a open circuit ZOC is equals to minus J Z naught cot beta L. Okay. Then what is the reflection coefficient and standing wave ratio of these open circuit transmission lines? So here also, so first I can recalling the definition of reflection coefficient delta L is equals to ZL minus Z naught divided by ZL plus Z naught. Now I can substituting directly this general L is equals to infinity, then again it will come same thing, that is undefined functions. Okay, so Z of L is equals to infinity and Z of L is also equal to infinity, then infinity by infinity is equals to undefined functions. So to overcome that one, first you can take the Z of L is common in the numerator and denominator. Okay. So Z of L is taken out 1 minus Z naught by Z of L whole divided by, in the denominator also Z of L is taken out. So 1 plus Z naught by Z of L. Now I can substitute Z of L is equals to infinity. So 1 by infinity, this term is 0 and this term is also equals to 0. Then 1 by 1 is, that is equals to 1. Okay. Now, so once we can find out this reflection coefficient, then the corresponding standing wave ratio S is equals to what? So S is equals to 1 plus del of L divided by 1 minus del of L. Del of L is equals to what? This one is, you can substituting here. Okay, so 1 plus 1 divided by 1 minus 1. So 2 by 0, that is equals to infinity. So therefore, del of L is equals to 1 and S is equals to infinity. See the difference of open circuit and short circuit. In the short circuit, the reflection coefficient is in negative. See, the reflection coefficient is negative and standing wave ratio is infinity. But in open circuit, the reflection coefficient is positive, but the standing wave ratio is infinity. Okay. Now, now we can recalling this ZOC and ZSC. That is, this expression ZSC is equals to J into Z naught tan beta L. Similarly, ZOC is equals to minus J Z naught into cot beta L. Now you can recalling these two equations and multiplying. Then, so Z naught into ZOC, while multiplying these two, then what will happen? So ZSC is equals to what? J Z naught tan beta L into Z1 is equal to what? This expression minus J Z naught cot beta L. Okay, so cot is you can write down in terms of tan, that is inverse. Okay, therefore Z cancels, J cancel, then tan beta L cancels. Okay, then what are the remaining terms? Here it is minus. So minus is you can while writing in terms of inversely multiplying and dividing in the numerator and denominator by j. Then j into j square. J square is equals to what? Minus 1 minus and minus plus. So it will comes only denominator is j. Numerator term is 1. So so remaining terms is z naught into z naught, that is z naught square. Therefore, Z naught is equals to square root of Z1C into ZSC. So the characteristics impedance of a transmission line is the square of the product of open circuit and short circuit impedances. That is Z naught is equals to square root of Z1C into ZSC. Okay, that is the expression. So can calculating the characteristics impedance from open circuit and short circuited impedances. Next. Next. Matched transmission lines. Okay. In a matched transmission line, now, so open circuit, short circuit, next, if it is a matched lines. So in the matched lines, now we can recalling the same expressions, that is Zn is equals to Z naught into Z of L plus. Aditya, is it audible?
Sir, yes, sir, audible, sir.
Okay, okay. Okay. Now, for a matched transmission lines, again you can recalling the expressions. So Zn is equals to same expression you can recalling for a lossless transmission line. For a lossy, then it will come tan H, hyperbolic functions. Okay, we are calling only lossless transmission line. So Zn is equals to Z naught into Z of L plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L. Now, so the condition of a matched transmission line, Z of L is equals to Z naught. That is the condition. Okay. For a open circuit transmission line, Z of L is equals to infinity. For a short circuit transmission line, Z of L is equals to 0. For a matched, that is load impedance is equals to the output impedance, that is Z of L is equals to Z naught. Now you can substitute in this expression, this condition in this above equations. Okay, now substituting this condition z of L is equals to z naught in this expression. So what will happen? So ZL is equals to Z naught, okay, plus J Z naught tan beta L divided by Z naught plus J Z naught. Now you can take Z naught is common. So you can take Z naught is common. Then Z naught, Z naught, Z naught polar cancel. Then what will happen? 1 plus J tan beta L divided by 1 plus J tan beta L. All are same. So entire term cancels. So it will comes only Z naught values. So at the time, the input impedance is equals to output impedances for a matched transmission line. Okay? Therefore, the reflection coefficient is equals to 0 because the input impedance is equals to output impedance. The waves cannot be reflecting back. Even you can applying this condition to the general expressions of the reflection coefficient. So reflection coefficient general expression is delta L is equals to Z of L minus Z naught divided by Z of L plus Z naught. Now I can substituting Z of L is equals to Z naught. What will happen? The numerator itself 0. Okay, Z of L is equals to Z naught. So Z naught minus Z naught, it is equals to 0. Okay, so the reflection coefficient is equals to 0. The waves cannot be reflecting back. Okay, then the corresponding standing wave ratio S is equals to 1 plus del of L divided by 1 minus del of L. So del of L is equals to 0. Then what will happen? S is equals to 1 by 1, that is equals to 1. Okay, therefore del of L is equals to 0 and S is equals to 1 for the matched transmission lines. Okay, so I can conclude that. So I can conclude that today's topics is a characteristics impedance Z naught value, that is R plus square root of R plus j omega L divided by G plus j omega C. Okay, that is first one. Then we can transmit. Now for a lossless transmission lines, for high frequency transmission lines, this R is equals to G is equals to 0. Therefore, characteristics impedance Z naught is equals to square root of L by C. Now, we can match these in output in characteristics impedance to the load impedances and input impedances. We are going to connecting the stubs. Going to connecting the stub matching. Okay, that is either single stub matching or double stub matching. Okay, next one. So this single stub and double stub matchings. Then there are some drawbacks. Drawbacks is it can certain ranges. The load impedances cannot be matched. And you can while going for increasing the more number of stubs, it is a complex. Then in the transmission lines, there are different transmission lines, whether it is a short circuit or open circuited or a matched lines. If it is a short circuited transmission lines, then the condition is Z of L is equals to 0. Okay, now while substituting this Z of L is equals to 0, then delta L is equals to reflection coefficient is -1 and standing wave ratio is equals to infinity. Whereas in open circuit transmission line, the load impedance is equals to infinity. then the corresponding reflection coefficient is equals to 1 and standing wave ratio is equals to infinity. Okay, now while multiplying these two, 2 minutes. So therefore, the characteristics impedance Z naught is equals to square root of ZSC into ZOC. Okay. So for a matched transmission line, Z of L is equals to Z naught. Therefore, load impedance is equals to output impedance is for a matched line, transmission line, the conditions, then the corresponding input impedance is equals to Z naught value. Therefore, for a matched transmission line, the reflection coefficient is equals to 0 and standing wave ratio is equals to 1. Okay. So next class can go for Smith charts. So any doubts? From the students' point of view? So any doubts? Okay. So today's topic is submatchings and transmission lines with open circuit, short circuited, and matched lines. Okay. So first deriving the expression for characteristics impedance Z naught, then open circuit transmission lines, short circuited transmission lines, and matched lines. So short circuited transmission lines, the condition is Z of L is equals to 0. Therefore, the corresponding reflection coefficient is equals to -1 and standing wave ratio is equals to 1. And input impedance Zn is equals to minus J tan beta L. Whereas open circuit transmission lines, Z of L is equals to infinity and the corresponding reflection coefficient is equals to +1 and voltage standing wave ratio is also equals to +1 and the corresponding Zn is equals to tan Z tan beta L. Then while multiplying these two components ZOC into ZSC, then so ZSC is tan beta J tan J Z naught tan beta L and ZOC is 1 by J cot beta tan beta L because tan is you can write down in terms of cot. So all tan terms is cancelled, J terms is cancelled, then it will come so only Z naught into Z naught, that is Z naught square. Therefore, Z naught is equals to square root of ZOC into ZSC. And the last case for a matched transmission line, Z of L is equals to Z naught. Therefore, the corresponding reflection coefficient is equals to 0 and standing wave ratio is equals to 1. So that is the today's topic conclusions. Okay, thank you.